Okay, so we got a velocity versus time graph, okay? And the first thing it wants us to calculate is the total displacement, all right? Once you get good at graphs, you'll be able to like look at a graph that looks like this one and know that the displacement is 0, okay? It comes down to not being so much calculating as recognition, okay? What does the object do for the first 5 seconds of this graph? It's not staying still. This is a velocity time graph. It's moving at a constant velocity of -8 meters per second, and it does that for 5 seconds. What's the last thing it does? Of +8 meters per second for 5 seconds. Do those two parts completely cancel each other out? What about these two triangles? Do they completely cancel each other out? This thing does exactly the same things backwards as it does forwards. Okay, so just in looking at that graph without having to do any calculating, I can see that it completely undoes what it did at the start. Okay, that the two parts, positive and negative, are exact copies of each other. All right, now if I wanted to actually do the math, I totally could. Okay, if I want to calculate the displacement for this section of the graph here, okay, I could do that, right? It would be -8 times 5, so that's -40 meters. Okay, this would be -8 times 5 seconds. Okay, that's 40 divided by 2, that's -20, and then the same would be true here. +8 times 5 is 40, +40 divided by 2 is +20, and then 8 times 5, okay, is +40. Okay, if I add all those things up, I got +60, -60, it adds up to 0. Everyone kind of follow me there? Okay. Sometimes you can save yourself work if you're good at interpreting a graph, being able to just look at the graph and go, oh wait, okay, it does exactly the same thing in both directions. All right, average acceleration. Yesterday we talked about this formula, VF minus VI over t. Okay, we can always calculate the acceleration of an object on a velocity time graph because we can always read these things. Okay, that is exactly what's on a velocity versus time graph. Okay, so between 5 and 15 seconds. Okay, so that means here and here. All right, so the velocity at 5 seconds would be my initial velocity. That's where this starts. Okay, so I'm going to say acceleration equals, okay, -8, okay, and then what's VF? +8. Okay, so VF minus VI, so 8 minus -8, right? And that happens over, from 5 to 15 seconds is how many seconds? 10. Okay, so 8 minus -8 is 16, divided by 10, that's positive 1.6 meters per second squared. Okay. All right, average speed over the whole trip, okay, is the last thing they want us to calculate. Okay, average speed is the total distance divided by the total time. Okay, so I know the total time is 20 seconds, so that I can put on here right away. Right? I did go through the bother of actually calculating what all of these would be, knowing I would need them for question 3, right? Or for question C, sorry. What's my total distance traveled? What do I do with the 4 numbers I put inside there? Add them up, right? Because distance is scalar. It doesn't care whether I went forward or backward, just how far did I go? Well, I went 60 meters here, and I went 60 meters here, so that means I went 120 meters in 20 seconds. Okay, so that should be 6 meters per second. Okay. Was there any really complex math in that question? Right? Like, we didn't even have to manipulate any of our equations. We just had to plug the numbers in. the trickiest part of a graphing question is the same thing that's tricky about a word problem. Figuring out what I have and what formulas I have to use to get to the answer. Okay? Remember, a graphing question is going to ask you to do the same things that a word problem asks you to do. It's going to give you the same information that a word problem gives you. Right? You just got to figure out what you have, your givens, and figure out what formula you need to use to get to the end. Okay? Ringing a bell a little bit from yesterday? Okay, so with velocity versus time graphs, okay, we will use this formula. Okay, with velocity versus time graphs, it does calculate acceleration. Okay, or I could just find the slope of the line. Okay, because when I have the slope of the line, remember on a velocity versus time graph, okay, that is that formula. Okay, it's Vf minus Vi over time. And that we can calculate the displacement, okay, by going average velocity times time. The little trick there is that's the same as calculating the areas of all the shapes between the line and the x-axis. Okay, we're going to spend today working on both kinds of graphs. Okay. All right, got a velocity versus time graph. It's very irregular, so y equals mx plus b will not come into play here. That's also something you should probably have maybe written down somewhere. If the graph is not one single straight line, y equals mx plus b is out. And anytime I give you a graph that is one single straight line, I will also give you its equation. So I will say y equals, okay, whatever the slope is, times x plus whatever the y-intercept is. I'll give you that. Okay? If you don't see that, then it's not in play. All right? So, using this graph, okay, I want you guys to see if you can answer, okay, those questions. Remember, these formulas are on your formula sheet, but I'll put them up here because they'll be useful. Okay, give you a few minutes on that one and then we'll go through it. I'm just going to grab something off the floor. So, it wants to know for part A the acceleration between 0 and 2 seconds. Okay, so if I'm going to find acceleration, I'm going to need final velocity. So that'll happen at 2 seconds. So here's 2 seconds. Vf is going to be 20. Okay, and at 0 seconds, well, that would be Vi at 0. All right, so now I know I can plug in for this. Okay, that it'll be 20 minus 0 divided by 2 seconds, right? Vf minus Vi divided by time. 20 over 2 is 10. Okay. Now remember, acceleration is a vector quantity, so that's going to be positive 10 meters per second squared. Okay. Now, something to be mindful of. I told you that this was a velocity versus time graph. Okay. You always have to make sure you know what kind of graph you're being given. What I did there doesn't work if this is a position versus time graph, because I don't have velocities, then I have positions. It's a mistake people make. They think they're looking at the wrong kind of graph. Okay? Always make sure you identify what kind of graph you're looking at. How many people are done B? Okay, I thought that one would take longer because there's a lot more work to do there. Draw your shapes. Lots and lots of shapes. Okay? So if we want to find the displacement between 0 and 8 seconds, this is as far as we are going. Okay, right to here. So in the first 2 seconds here, object is accelerating. Okay, so that's going to make a triangle. That will represent its displacement because its average velocity will be half the height of this triangle. So I'd still be going d equals v times t. Okay, so that's going to be 2 seconds times 20, so that's 40, divided by 2 is positive 20 meters. Okay, and then you got a few options on how to draw the rest of the shapes. I usually try to draw as few shapes as possible. So what I'm going to do is draw a rectangle that goes all the way across like that. A triangle here, and then I'll have this rectangle on top of that. If you drew it differently, that's fine, as long as you get the same total area you'll get the same answer I do. Okay? If you broke it up differently, totally fine. All right, so this box here goes from 2 to 8 seconds, so it's 6 seconds on the base. It's 20 meters per second high. Okay, if I travel at 20 meters per second for 6 seconds, I'm going to travel 120 meters. Okay, this little triangle here, okay, I'm going from 20 to 40, so the height there is 20. Okay, and then I'm going to divide that, I'm going to multiply that by the 1 second here, so 20 times 1 is 20, divided by 2, okay, is positive 10 meters. All right, and then I've got this box here, it is 20 high by 3 seconds, so it would be positive 60 meters. All right, so 190, 210 meters. Okay, and that answer there would be wrong. Why is the answer I have written, even though 210 just came out of my mouth, why is that answer wrong? The number's right. The answer is wrong. Why? No, the units are fine. Meters is displacement. So I'd use meters for that. It doesn't have a plus. Is displacement a vector quantity? Is this thing moving forwards? Okay. I'd at least have to write a positive there at the bare minimum. I could also write forwards. Okay. Sometimes, and this is something to watch for, on the graph, they'll actually put like north beside the label for the axis. Always be on the lookout for that. Okay. If they do that, then that's the vector you'd have to put on there. Okay. This graph obviously doesn't have that, so we would just write positive in there. So to make that the correct answer, positive 210 meters.
If it were capital, where would you write that instead of?
You would have to write north then, yes. Okay. Positive would actually be wrong in that situation.
So would you write it before the note?
Yeah, direction, so the order that you would write things in is magnitude, units, and then if you're writing a direction in words, you write it last. If you're writing positive or negative, obviously the convention is that comes before the number. Yeah. Okay, for part C, how many people have done C? Okay, so why is the answer 0 for the acceleration between 10 and 11 seconds? So that's that section of the graph right there.
Would it be because it's not really like going up?
Right.
It's just like flat line.
It's traveling, yeah, it's a flat line, which means it's traveling at a constant velocity. Acceleration is a change in velocity. Velocity is not changing here. Okay, so that's not necessarily a math question, although you could solve it mathematically if you wanted to. Okay, you could go A equals BF, 20, minus VI, 20, divided by 1. I mean, you can do that and get 0, or you can look at it and go, I know that acceleration means the velocity has to change, and it's not changing there, so I'm just going to write 0 and be done with it. Either way, you get the right answer. Okay, I would be more impressed if you just wrote 0 because you recognized it wasn't accelerating. I'd probably be less impressed if you wrote the math like I just did there. Okay, because that means, hey, I can interpret a graph. Okay, not that the other way isn't perfectly valid, it is, but I'm more impressed by you understanding a graph. Okay, all right, how many people are done D? All right, I'll give you a little bit more time on D and E. Okay, you've done, like we've got some of the numbers on here, so you know some of the work is kind of done for us there. We don't have to do everything over again. All right, so for D, it wants the average velocity between 0 and 10 seconds. All right, so if we're going to get the average velocity, we're still going to need these two shapes, okay? Because we need to know the displacement to 10 seconds. We've only calculated it to 8, okay? So we do have to do a little bit more geometry, okay? So the height of this triangle here goes from 20 to 40, so it's 20, and it's over 2 seconds, so 2 times 20 is 40, divided by 2 is 20, okay? And then this box down here is 20 high by 2 seconds. So we got to add another 60 meters to the 210 we already calculated. Okay, we don't have to do it all over again. We just have to add another 60 meters, okay, to the 210. So average velocity is total displacement divided by total time. So that's 270, positive 270 meters, divided by, obviously, 10 seconds, okay, from 0 to 10, and that's going to give us positive 27 meters per second. Okay? All right, how many people have done E? All right. So for E, we just have to finish off all the shapes. Okay? So what I would do is just go all the way across to get that rectangle. It's identical to this one, so it's also 40. Again, that's a recognition thing. It can save you work. Okay, those two triangles, or rectangles, sorry, have the same dimensions. Okay, this triangle here is 10 high by 1, so 10 times 1 is 10, divided by 2 is 5. So we got to add another 45 meters to the 270, okay, and we'll get 315 meters. Okay, questions on any of the parts of that graph? Okay, so you have some idea what my expectations will be on a quiz or an exam. Okay, I probably wouldn't give you one that would have this many parts on a quiz or a test. Maybe a quiz, but definitely not a unit exam. Okay, because it would take too long. But I would ask you to do all of these things on a velocity versus time graph. Okay, I would probably just make the velocity time graph shorter, like I might end it here at 5 seconds instead, so you wouldn't have as much kind of tedious work to do. Okay, but those are exactly the things I would ask. Oh, did I not put them up? Okay. 5, 6, 6A, 7. Yeah, 5, 6, 6A, and 7. Those would be the ones I would try. Okay?
Is there quiz double-sided?
Are they what?
Is it double-sided?
Friday's quiz?
Yeah.
Well, because I wanted to make the graphs big, yes. Yeah. Okay, any other questions on that one? Okay. All right, so this one, it's got less parts. This one would probably be more like what you would see on a quiz. On an exam, I'd probably still make it shorter than that. Okay, so you've got a velocity versus time graph there. Okay, let's see if we can get those 4 things. They're basically the same things I asked you on the last one. Okay, just practice here, right? So we can do this together, okay, and kind of go over it and see how we're doing. Why is the answer for A negative? Okay, and she pointed out it's still going forwards, and you're absolutely right. Okay, the velocity is still positive. Everywhere on this graph, the object's moving in a forward direction. But if you're going to go from a velocity of 3 meters per second to 0, you have to accelerate backwards. To slow down, you actually accelerate backwards. That's actually something that in North America we have trouble with because we usually use automobiles to get around, okay? And we press the brakes, okay? Pressing the brakes exerts a force backwards. That's why we slow down. But it never makes your car go backwards, okay? But think about this. Let's say I put a bungee cord across the front of the classroom here. If I run at that bungee cord, okay? I hit that bungee cord. I'm still moving forwards, but I'm accelerating backwards. The bungee cord's pushing me that way. That's why I slow down, right? My velocity becomes less and less positive until I get to 0, and then I get shot back the other way.
But how did we get 1.5? Because I thought it would have been like negative 3.0 because it's.
But it happens
going
over
down
how much
all the
time?
way. So 2 minutes.
It happens over 2 seconds. Okay, so look at it this way, right? How do we cut? What's the formula for acceleration?
I don't know
Minus initial velocity divided by
Time.
time. That's where the 2 comes from. That's why it's 1.5. Right? So we go, final velocity is 0, initial velocity is positive 3, and that takes 2 seconds. 0 minus 3 is negative 3. Negative 3 divided by 2, negative 1.5 meters per second squared. Yeah? Okay? Does everyone kind of follow what we did there? Okay, I love the analysis. Like you were looking at that and going, but they're going forwards. You're absolutely right, they are. But they're slowing down. And to slow down, you have to accelerate in the opposite direction. Okay, let's have a look at B. Okay, so we want to know the total displacement between 0 and 7 seconds. So we're going this far. Okay, so in that first second, okay, the object accelerates, and then it travels at a constant speed, but I'm just going to draw that rectangle all the way across, and then I'm going to make those other 2 shapes, and then I think I'm covered. Okay, so for this first second, okay, it's 1 on the base by 1 high. 1 times 1 is 1, divided by 2, positive 0.5 meters. This rectangle goes from 1 to 7 seconds, so it's 6 seconds long. It's 1 high. That's positive 6 meters. Okay, this triangle is 2 on the base and 2 high, so 2 times 2 is 4. Okay, divided by 2, positive 2 meters. And then this rectangle here is 3 by 2. Okay, so 3 times 2 is positive 6 meters. All right, so if I want to get my total displacement there, it's going to be 14.5, positive 14.5 meters. Okay, 6 plus 6 is 12, plus 2 is 14, plus 0.5 is positive 14.5. Okay, if I want to get the average speed over the whole trip, okay, speed is total distance divided by total time. Do I have the total time? Okay, this whole trip takes how long? 10 seconds. Okay, so I know I can put 10 seconds over there. Okay, I'm missing one part here for the distance. I've got to get this triangle here, okay, to complete my total distance traveled. So it's 2 seconds on the base by 3 high. 2 times 3 is 6 divided by 2. Okay, that triangle is another positive 3 meters. So my total distance is going to be 17.5. Without a positive on it, because distance is scalar. Okay, now I had a good question here while you guys were working on it about, do I have to worry about this being positive, this being negative? On this graph, no you don't. This object only moves forwards. Okay, so in this graph, the displacement of the object and the distance it travels are the same because it never changes direction. The only time you have to worry, okay, about distance and displacement not being the same number is if the object actually does go backwards. If it does, then displacement will be smaller. Okay, distance will be bigger. All right, the last thing the question wants is the acceleration between 2 and 4 seconds. So that's starting here and ending here. All right, formula for acceleration, Vf minus Vi over t. Okay, we already know that between 2 and 4 seconds, there are 2 seconds. All right, so we got the bottom already figured out. Okay, Vf is 3. Vi is 1. 3 minus 1 is 2, divided by 2, okay, is positive 1 meter per second squared.
Why is it like C up and then towards 75?
I must have divided it by 9. Is that what I did?
Yeah.
Okay. Because I redid the graphs last semester, and I think I ran this one to 10 when I was supposed to stop it. So, yeah, that should be, you're right, absolutely. It should be 1.75. Yeah. Okay, any other questions? Good eye on that, Julie. Okay, any other questions on that one? Okay. Okay, what kind of graph is this? It's a position versus time. See if you can switch gears now. Okay, because that's what you're going to have to do on a quiz or a test. Oh, this is the position time graph. What do I do? Okay, this is the velocity time graph. I do something different. All right, so give this one a try here.